Hi everyone, I'm Dominic. I'm a student of Nick and Nick, and this is Bandlimitation, wavelets, and Scaled QFT to work with the RMIT, but also in collaboration with some people from Macquarie, namely Simon and Dan. Dan is here, Simon and online, Gavin as well, and also Aki was probably asleep. So I just want to talk a little bit about motivation for bandlimitation. In the first place, Nico mentioned it a little bit just before. This is not just covariant but non-covariant as well. But from quantum gravity, we have this notion of a maximum resolution for space-time measurement. It comes from just the thought experiment. If you combine Einstein's equations with an uncertainty principle between two P's, you end up with this notion that you have to have this finite minimum length scale at the end of the day. Similar thing comes from black hole thermodynamics. We talked a little bit about it this morning, and Hawking radiation, entropy. We also have this notion of it from QFT, just with regular ultraviolet cutoffs to our fields and renormalization. We have this idea that everything seems to point to this idea of a minimum length scale. And there's a question then, how can we incorporate this into our theories such that we still maybe have continuous, like notions of continuity in our QFTs, but also still have a minimum length scale as well. And regular non-covariant bandlimitation gives us an avenue towards this. So, just talking a little bit about bandlimitation from signal processing. Some of you may have heard this before, maybe multiple times. But if we have a signal, just a regular classical signal that is band-limited, and thus has a finite Fourier domain, let's say symmetric, then equivalent to an ultraviolet cutoff at omega, and currently no infrared cutoff, it can be constructed from a lattice of its samples. So you can have an exact equivalence between a continuous function and a set of its, an infinite set, but still countable, of its discrete samples. And that usually comes from Shannon's sampling theorem. Here the samples are equidistantly spaced. We don't necessarily need that, they just have to be sufficiently dense over the region that you care about, the region of space, the region of space-time, depends on what you want to look at. But we can reconstruct it just with Shannon's sampling theorem or any sort of interpolation function, depending on how our samples are spaced. And this sort of thing is done commonly in animation, where you have something that's at low frequency, it's interpolated for something at high frequency. It doesn't necessarily need to be a continuum, but we can do that. You just end up with a band-limited signal, or band-limited video, yes, in the animation case. But what it means is that we could have a discrete function and a continuous one, and have them be effectively agreeable at every scale through band-limitation. And what that means is we can push this idea and take normally intrinsically continuous notions, such as calculus, derivatives, integrals, products, everything like that, and give them exact equivalent discrete representations, if only considering band-limited functions. So, I just said that. But we can take the reconstruction formula, just with this S now being a sinc function, so Shannon sampling, and just take its derivative, and get some equation for the derivative of a band-limited function. This is an exact derivative so long as the function remains band-limited, and it's just a linear combination of the samples. So these are just numbers, this is just the function's nth derivative at a point, and this is just its values. So you're just taking linear combinations of the function's values, and you get its derivative. And I've just said that as well. I need to figure out how this animation is going to work. But if we were to look at what this derivative looks like, it's this sort of oscillatory thing. These are these values of d, this first derivative. They decay polynomially. Turns out they're linearly for the first derivative, quadratic for the second, etc. The polynomial decay is the power of the derivative. But you can calculate it through this. But for specific cases, they end up being these values here, which when plotted have this oscillatory behavior, but also this linear decay of inverse decay. We can do a similar thing for inner products, write a discrete equivalent inner product, and we find that our sinc functions are orthogonal to each other, and the result of that is that you can apply it to just the product of any two functions, like any two band-limited functions under an integral, and end up with that just being the Riemann sum of their samples. So the integral of the product of two bandlimited functions is just the Riemann sum of their samples. This will be useful because now we can look at that and just treat it on just a standard Klein-Gordon field and just follow the same prescription. Nico talked about it a little bit. All we end up doing is just projecting the momentum states down to only a finite region between, down to a finite band, in the same way that you might do just with some sort of projection, or just implying that any momenta beyond your cutoff just don't exist at all. The actual Fock operators, the ladder operators, don't change, but the commutational relations do. We now end up with a sinc commutator instead of a Dirac delta. And if we were to take the band limit back to infinity, we would recover that Dirac delta commutation relation. It just looks like this. It's non-zero at longer ranges now, so it's no longer local. But if we look at just the integer lattice spacing, or integer multiples of lattice spacing, we still have locality if you consider only a lattice. So it's local if we only consider lattice sites. We can do the same prescription with its Hamiltonian and write it in terms of band-limited fields and see that this is just derivatives and integrals of band-limited functions, which we can use our techniques for, and write this as a discrete sum of the field's operators. It's just constant momentum and the field. And we can see that we have a lattice model for the continuous quantity of the Klein-Gordon Hamiltonian. It's non-local, but it's still a lattice model, so we can sort of treat it as a lattice of coupled harmonic oscillators. Despite appearances, this spring coupling is not local. It's not even nearest neighbor. It follows that discrete derivative coupling, and so it looks a bit like this. It decays quadratically, but it's still oscillating. It's not local. There's a few things you can do to try and make it local, but if you just treat everything for now as the way it is, you end up with non-local coupling between oscillators. Again, it decays quadratically. But what it means is that if you have a band-limited and continuous theory, like this one, you can always find an equivalent lattice theory that will tell you the exact same physics. You don't have to try and interpret what this coupling sort of means, but it means that you can have just a lattice theory that gives you the same physics as the continuous one. And this actually has been looked at quite a bit, particularly in the 80s and 90s with just lattice QCD calculations that do a similar thing. But the question is, how far can we take this notion? And one of the ways is, well, can we follow a similar prescription with functions that aren't band-limited, or fields that aren't band-limited? Can we take them and decompose them into just a whole bunch of smaller band-limited ones? And the answer is yes, we can. And we can do that with leveraging our ideas about band-limited models with what we call Shannon wavelets. And this is me moving from my Bandlimitation project to the Shannon wavelets. So, what are Shannon wavelets? They're really just another tool for functional analysis and image processing and signal processing that let us look at things in different ways. So we use them to decompose an image into different resolutions. It's image processing. Let's say, for instance, you take an image with some amount of detail and you decompose it into a high resolution, low resolution, and medium resolution components of an image, and that you could then store and later combine into the full thing later on. This is actually how JPEG image compression works. You decompose it from some sort of wavelet basis, maybe like Shannon one, and that lets you look at different components of your image and then signal and image and signal in different regions. So in signal processing, we do the same thing. We decompose things into frequency regions, like low, medium, and high, and then you can later reconstruct the whole thing just with some sort of reconstruction point. So let's do it with more than three signals like this, with a center band here, and a whole bunch of extra bands outside. So this is the bandlimited component, with just a finite, almost ultraviolet cutoff, and a whole bunch of extra wavelet components. Right. And all we've done here is just deconstructed the Fourier spectrum into just a whole giant sum of smaller components. So here, omega is no longer an ultraviolet cutoff, it just sets the width of each band. And then if you want to add them all back together, you just recover the whole spectrum. You've really not really changed anything, you just chopped something up to later put it back together. And the width of these bands increases for increasing scale, but that's fine. So, for now, just consider a function whose Fourier domain is only non-zero within one of these wavelets, so within these two bands. And so you write it like this, and this is these two are equal, so the Fourier spectrum is only defined over the bands, and like a Shannon reconstruction formula, this will have a wavelet reconstruction. So you can write the continuous function g just as this linear combination of wavelets with its values on some sort of lattice. Psi here, here again, and we can just do again reconstruction similar to Shannon, just with these new functions instead of sinc functions. They're just wavelets, which are the difference between two sincs. These coefficients are given by the values of the function on a lattice of spacing now no longer delta x, but 2 to the minus n. And they're basically just the samples of g. Again, what that means is that we have a sampling theory for this banded function. And by the ability to decompose any function into a whole set of bands for its Fourier transform, you can create a sampling theory for any function, whether it's bandlimited or not, just by doing this decomposition and writing it in terms of its bandlimited component and its scaled components, each of which has a sampling theory. And that means that you can take this scaled decomposition of a function, divide it into its individual sampling periods, and then put them all back together and write a full sampling theory just for the non-bandlimited function. This now has the sum of the function samples on one lattice plus an infinite sum of its scales, different scales, at all of these different lattices of different densities. Just one thing to note that these wavelets are orthogonal in both scale and displacement, and this similar thing, they have no overlap with the sinc function. And so,
discrete well, okay, scale it. Yeah, you can't scale it too much, right?
no, it's not. This is the discrete. So,
discrete in scale is continuous in space and not discrete in space.
Yeah, so it's discrete in space, discrete in scale. And then through reconstruction, you can make them continuous in space, but they're still discrete in scale. But we can see that as these are all orthogonal, each component of reconstruction gives unique information function. So if you want to reconstruct the whole thing perfectly, you need all of these values at every scale. Rush through this, but analogous to the bandlimited case, all of these wavelet decompositions at each scale has equivalence to the derivatives, both for the bandlimited part and the wavelet part. The coefficients are a little bit different, but they're kind of similar. They still decay polynomially with distance and position. But we can write this full generalized discrete derivative as a linear combination of the bandlimited functions values plus the linear combinations of the scaled function values. This is again a fully discrete theory. It's just not one-dimensionally discrete. It's not two-dimensionally discrete. Just something we'll talk about a little bit later. For the first derivative, these look like this. They still decay linearly and they still oscillate, but now they don't cross zero. So they're massive ahead of this regular bandlimited. Again, for the sample prescription product, and write an inner product of true functions in terms of now a whole bunch of Riemann samples of different lattices of each scale. said that. But as we can see, there are no cross-scale terms, so you don't need any multiples of two different scales, just all at one. So we can again apply this to the Klein-Gordon field. So like a regular free scalar field, we can decompose it into different scales, and we'll see that these values are at different points in different lattices. Like so, the field values at each scale are at lattices of different spacing. So each component of the field has a sampling lattice of oscillators with spacing given by either pi on omega, which is that's the width of the scale, or 2 to the minus n times by the same spacing. The commutation relations are again modified, so at each scale, or at different scales, the field is conjugate momentum always commute, but on the same scale, so phi and phi and again, we end up with this Kronecker delta that shows that at different scales they commute, but at the same scale they have this difference of sinus commutation relation, which is a Kronecker delta on lattice spacing, but non-local everywhere else. We do the same thing for the Hamiltonian, and we end up with a band-limited component and a scale decomposition for the rest of the modes, the rest of the frequencies. But again, there are no cross terms between scales, and because of that, we can make a few observations. First, the full non-band-limited Klein-Gordon field has this Hamiltonian, which is just the sum of all of the constituent ones, which makes sense because we've really just written the whole thing into this big orthogonal basis. The constituent band-limited and scale fields have their own respective Hamiltonians that do not have any effect on any other at any different scale. So there are no cross terms between the scales, and so each Hamiltonian on its own describes all of the physics at each respective scale and tells you nothing about everything else, and that applies for the whole theory. And so what that means is that if we recall that the band-limited Klein-Gordon field has this equivalent lattice model, well, you can, and it's a model of non-locally coupled harmonic oscillators, the same can be said for the scaled Klein-Gordon field at each level. And again, this is also a model of non-locally coupled harmonic oscillators, just with different type of coupling, still quadratically decaying. But we can now put all of these layers on top of each other to sort of try and build this two-dimensional lattice of oscillators, where now this is a dimension in our regular position that's been discretized by each cutoff, and now this is a dimension in scale. And if we wanted to naively treat this scale dimension as just another spatial dimension, we could try that. So again, we have non-local coupling between the oscillators at each scale, zero coupling between the scales, which will be important later. But the total Hamiltonian takes into account all of these 1D lattices, and so you can write the whole thing, just draw it as a 2D one, just by putting them all on top of each other. And so on each lattice, on each layer of the lattice, everything is governed by the Hamiltonian at that scale. Nothing has any effect on anything else. And between the lattices, between the layers, everything behaves similarly, just with different parameters that determine how closely things are coupled to each other. Under this decomposition, the question is, can we infer the geometry of such a lattice if we were to consider scale as just another spatial dimension? And so the distance between each oscillator is set like this. It's 2 to the negative n pi on omega, and the question is, how do we quantify this cross-scale distance? And the answer is with correlation functions, or with cross-scale correlations. This is analogous to something that Akeem spoke about last year, and also a little bit in July of this year at RQI North. And there's this idea that when we consider distances, normally we would consider the metric, space-time distances. But it turns out that you can determine this metric by taking derivatives of the inverse of the Feynman propagator. It's the dimension, so it's 2 over 2 minus 4 dimensions. inverse square of the Feynman propagator, you take its derivatives, and you end up with components of the metric. And so, if we wanted to try and infer some sort of geometry about this lattice, well, we'd have to ask ourselves, what is the correlation function between here and different points and different layers of this lattice? Again, this is just a time-watch correlator, Feynman propagator. However, there's a problem. If we recall that the lattice has no coupling between the layers, we may also be able to note that this two-point correlator, which will just end up taking into account an integral over the overlap over the Fourier domains of the different scales, we can note that just from this picture, there is no overlap between the Fourier domains, or basically by definition, because we use the Shannon wavelet, which requires no overlap between the scales. And so, if there's no overlap in the domains, the correlator will always be 0 in between the scales. And what does that imply? Well, it implies that we have this almost infinite separation between scales if we wanted to treat this scale as an actual distance metric. It would mean that one lattice, no matter where you draw it in a picture, would be infinitely far away from each other 1D lattice. It's like they're completely isolated. They can have no interaction with each other. And it turns out we did all this for the free field. It turns out that happens again even for interacting fields. I'm not going to do it just time-wise. But it means that we have this notion that there's infinite distance between each layer. So, to summarize, we have perfect equivalence between discrete and continuous band-limited QFTs. Band-limited theories will always have an equivalent lattice theory. And we can decompose non-band-limited fields into band-limited ones using these wavelets, and then each of those will have their own equivalent lattice theory. There may be some applications towards defining a Lorentz covariant way of doing that, so that you can have Lorentz covariant limitation. I haven't thought about it too much yet. So. But you can write a non-band limited QFT as an equivalent two-dimensional lattice model. But for Shannon decompositions, at least for Shannon wavelets, it's a little bit tricky to define distances between the layers of the lattice. For other wavelet types, it's a little bit easier. Which time we can talk about it this afternoon. Thank you.